Alright, so this is your standard disclaimer that tells you that you're being recorded right now, and staying in the meeting essentially means that you consent to being recorded. Alright, go ahead, Anna.
Cool. Can anyone define a mineral for me?
It's a solid, naturally occurring, not organic thing.
Yes. And you're missing
bunch of molecules compact together to make a solid form.
kind of, yes. I usually listed like 3. There are 5 I guess criterion for a mineral. So does anyone like know the other 2?
So we have solid, inorganic, and naturally occurring.
Yes.
The only exception is mercury, which is liquid, but that's it.
It depends on whether or not you would define. But like, since mercury, like once it's like not liquid, because it's only liquid at certain temperatures, right? And you could technically argue that, for example, ice, which is a mineral, is also liquid at other temperatures. Okay, so the other 2 criterion are like they have to have an ordered crystalline structure. So there has to be like some structure to all the molecules. And then there also has to be a definite chemical composition. So something you're going to notice is that ice like fits all of these. So like people generally consider ice a mineral, which is kind of, I guess, not intuitive. So
What are the things? Are there 5 definitions of a mineral again?
okay, so a mineral is naturally occurring, and it's inorganic. It's a solid substance. It has an orderly crystalline structure and has definite chemical composition. Okay, so all minerals like have some properties that like you use to like identify what a mineral, like which mineral it is. So under optical properties, we have luster, the ability to transmit light, color, and streak. So luster is how like a mineral reflects light. So it can be metallic, non-metallic, pearly, silky, greasy, glassy, etc. So actually a lot of the things that we like use to describe a mineral's texture or how it looks is actually goes under luster. So these are like the picture here like shows some of the examples of some common lusters and the words that are generally used to describe them. And then we also have the ability to transmit light. So this is like opacity. So like opaque means it doesn't transmit light at all. And so you can't like see through it basically. And translucent is like wax paper. You can kind of see through it, but it's not completely clear. And transparent is it's clear like glass. And then the third optical property is color. And generally when you're identifying a mineral, you're not going to go for color because like there are like 20,000 different minerals of like each color. So color is kind of not reliable. And then you have streak. So streak is kind of like color, but it's like when you rub a mineral against a streak plate, which is like it's usually a fire plate of like clay or something like that. And when you rub against it, the powder, it leaves a powder and that powder will have a color. So that's what streak is. But like for rocks that are harder than like the plate that you're rubbing against, obviously you're not going to get any streak, right? Because they're not like going to leave any powder. So that's one of the things that like a streak plate doesn't really work for. Does anyone want me to stay or can I move on?
Please stay on it for a second.
Okay. Can I move on now?
Yeah.
Cool. Okay. After this, another property of minerals is like its shape, or specifically its crystal shape and its habit. So of course, since a mineral can like come in alternate shapes depending on like how it's broken, that's not something that you're going to use to identify a mineral. But you can identify a mineral through like how its crystals inside the mineral have been formed. So each, like some minerals will have a characteristic shape of crystal growth. So for example, magnetite will generally grow in like octahedrons, and then garnet will grow in dodecahedrons, and halite and fluorite, halite is like table salt, right? And you can tell like it grows in cubes. So some common terms to describe like crystal habits or shapes is basically like prismatic, platy, blocky, banded, granular, equidimensional, stuff like that. And then you can note that some minerals have two different habits. So for example, pyrite has like this one, which is kind of hexagonal or pentagonal, and then this one that's more cubical. Can I move on?
Sure.
Cool. The third attribute of a mineral, I guess, is its strength. So this is measured by Mohs hardness scale. And you guys probably all have heard of this, hopefully. And so I think most people know that diamond is like the hardest, and talc is the least hardest, the weakest. So in order of like some minerals that are specifically like attributed to a number, talc is 1, gypsum is 2, calcite is 3, and then you have fluorite, apatite, orthoclase, quartz, topaz, corundum, and diamond. So that's like the order of hardness that you have. And I guess most people generally remember just that like talc is the softest and diamond is the hardest, and quartz is decently hard. I think those are like ones that should be remembered. But also connected to mineral strength is cleavage. So it's like whether or not the mineral has some weak points. So for example, mica, like it cleaves directly in plates. So there are weak points, like kind of like parallel to its shape. And then some other examples of cleavage are shown in this picture. So there are actually a lot of different ways that like a mineral can cleave. So then a fracture is what happens when a mineral doesn't have any like ordered weak points. So it's not going to have cleavage, and it's just kind of going to like break against random lines if you hit it hard enough. And then tenacity is the resistance to breaking or bending. So generally metals are very malleable and elastic, and usually like things that you think of as brittle are like things that kind of like shatter. So generally, actually, minerals that are brittle are like non-metallic minerals. I guess you can think of it as that. Okay, so other properties that are not specifically under, wait, did I skip? Oh yeah, okay. So the third property is going to be density and specific gravity. So density is the mass per unit of volume, and specific gravity is how much the mineral's weight is compared to the weight of an equal volume of water. So usually for a mineral, it's going to be 2 to 3. So their specific gravity is going to be 2 to 3. But for minerals like of iron, then this specific gravity is going to be like extremely large. So some exceptions are galena, which is an ore of lead, and has a specific gravity of 7.5, which makes sense because a lot of people think of lead as like super heavy, right? And then 24 karat gold has a specific gravity of 20.
I always thought of lead as like the heaviest.
Yes.
Well, technically,
Also-
tungsten has more mass per cubic centimeter.
Yes, but also gold is kind of like you're not gonna like get like a huge chunk of 24 karat gold. So you usually can't really like compare its specific gravity. And to like measure specific gravity, you kind of just like lift something and you like feel if it's heavy compared to like similar sized rocks, right? But you're never going to get a 24 karat gold chunk the size of like other rocks. Hopefully. Or sadly, you're never going to get a 24 karat gold chunk that is the size of similar rocks. Okay, so other properties. Some properties include taste, which is like salt, right? It tastes salty. And then you have texture and feeling. So some notable examples are talc, which feels really soapy, and graphite, which feels super greasy. Like if you touch the tip of your pencil, it doesn't feel like, it feels greasy basically. And smell, so for example, sulfur, it smells like rotten eggs. And also like iron content. So magnetite can be picked up with a magnet. A lot of things with iron content can be picked up with a magnet. And then it's one property that I find kind of interesting is optical properties. So for example, calcite, like you can see in this picture that it has double refraction. So essentially if there's like one line, it refracts it into two lines. So for example, glass, like if you have one line and you put a piece of glass on top of the line, it's only going to show that one line, right? But for example, calcite, it's going to show like double. And then another property is reaction to acid. So specifically carbonates, so minerals with CO3 2- will like fizz because they're releasing carbon dioxide when they like get reacted with acid, I guess, when you put acid on minerals with carbonate. Does someone want to say something? No? Okay.
Is this why Uranus smells like rotten eggs?
Does Uranus smell like rotten eggs?
Yeah, that's what a lot of articles I've read have said. Because they have like sulfur dioxide or something there.
And probably, yeah, if it has sulfur, then it's going to smell like rotten eggs. Wait, hold on. Lucas. Wait, what? Okay, we're not. That's fine. Cool. We're going to ignore what he just said because we're not talking about ohms. I think that was what he was talking about. Okay. So mineral groups. Yeah, I realized. Okay, mineral groups. So we have silicates, and silicates are like silicon plus oxygen, and it's 4 atoms of oxygen and 1 atom of silicon, so SO4. And because there's so many silicates, they are split into light silicates and dark silicates, because like most minerals are considered silicates. So light silicates are obviously light in color, and they have a general specific gravity of about 2.7, and they can contain aluminum, potassium, calcium, or sodium. So note they don't contain like iron, because iron is going to make the specific gravity like a lot larger. And so the groups under light silicates are feldspars, quartz, muscovite, and clay minerals. So feldspars, the numbers here are its hardness on the Mohs scale. So feldspars have a hardness of 6. And under feldspars, we have potassium feldspar and plagioclase feldspar. So potassium feldspar obviously contains potassium, and plagioclase feldspar contains calcium and or sodium. So the way you differentiate between these is that you're going to have striations on plagioclase feldspar, and you're not going to have striations on potassium feldspar. So we can see that, for example, this is going to be a potassium feldspar because it doesn't have like striations, which are basically lines you can kind of see on a cleavage surface. But this is going to be plagioclast feldspar because you can see like the horizontal lines and it's kind of clear. And then I think everyone is kind of familiar with like quartz. And then muscovite is part of the mica family. And I think a lot of people are also familiar with the micas. Question. Or someone just unmuted. No? Okay, never mind. And then clay minerals are minerals that like make up the soil. And so there's a lot of light silicates in the soil. So an example of like a clay mineral is like kaolinite. So it's like, it makes this white clay when you fire it called kaolin. So fun fact. The dark silicates. So the dark silicates are also have the silicon oxygen tetrahedron, of course, because it's a silicate. And since they contain iron or magnesium, they generally have a much higher specific gravity than light silicates. So these have a 3.2 to 3.6 specific gravity. So under dark silicates, you have the pyroxenes, the amphiboles, olivine, biotite, and garnet. So for pyroxenes, the most common is augite. You can see this rock here is augite. For the amphiboles, the most common is hornblende. And hornblende is actually the dark part of a lot of light-colored igneous rocks. And what you're going to notice is that hornblende and augite look remarkably similar. And that's because they are similar, but they have different like cleavage. But that's the only way you're going to be able to differentiate between hornblende and augite, unless you actually like get down to the molecular level. And then olivine is also a major constituent of dark-colored igneous rocks, and it's also found in the upper mantle, and it has a glassy luster. So biotite and then you have biotite, which is part of the mica family too. So you're going to notice that you have a light silicate muscovite under the mica family, and you also have a dark silicate biotite under the mica family. And then you have garnet, which is just like garnet. Or garnet has like a glassy luster, and it's usually found in like, or when it is found in deep red, it's usually like used as a gemstone. I think I went to this rock place once and I got a piece of garnet and I thought it was ruby. And that was sad because I realized it was garnet like afterwards. So after the light silicates and dark silicates, you're going to have non-silicates, so ones that don't include SiO4. And so under the non-silicates, you're going to have a lot of different like chemical base formulas. So for example, you have the oxides, which have oxygen, and these include like ice, which is a mineral. And then you have the sulfates, which have SO4 2- or -2, and then these include gypsum. And then you have carbonates, which like calcite. And note that earlier we talked about how carbonates will like fizz when it reacts with acid. And then you have the halides, which can be Cl-, F-, or bromine Br-, and it includes fluorite. Also includes halite. So you can see like there is fluorite isn't pictured here, but this is halite. And then you have the sulfides, which include pyrite. And then you have those elements that are like, for example, gold, diamond, which is like carbon, and then copper, sulfur, graphite, which is also carbon, silver, and then platinum. And these are like these are minerals that are made of like only one element. Okay, rocks. Because minerals make up rocks. And rocks are cool. So I hope people are familiar with this graphic. So this is the rock cycle, and it connects the igneous, sedimentary, and metamorphic rocks. So you have like sedimentary rock if it goes under extreme pressure, or any rock if it goes under extreme pressure or like heat, it's gonna like turn into a metamorphic rock. And if any rock is weathered and then like the weathered parts are like glued together, it's gonna turn sedimentary rock. So you're gonna see that all rocks kind of like they change from rock type to rock type periodically because of like weathering or because of like they get buried and get under intense pressure or heat. So igneous rocks. So igneous rocks are from cooled magma or lava. Lava is magma on the surface, and I think you should differentiate between those because there are scienceful questions asked on that. So there are two types of igneous rocks, extrusive and intrusive. So extrusive basically means it's cool lava. So the magma got to the surface, for example, from a volcano or from just like cracks in the crust, and it cooled. And so extrusive igneous rocks are generally going to be a lot more smooth, and the reason is because they're going to cool a lot faster, right? Because like the temperature outside of the mantle is going to be a lot, or outside the crust is going to be a lot more cold than like the temperature inside the crust. And then intrusive and plutonic igneous rocks are generally more rough because they took a lot more longer time to cool, so the crystals have a longer time to form. Also, another way to like categorize igneous rocks are by granitic or andesitic. So granitic is like you have more light silicates, and in these rocks you have only about 10% of dark silicates, and so granitic rocks make a major part of the continental crust. And then you have the basaltic or mafic rocks, which are like at least 45% dark silicate, and they make a major part of the ocean floor, and basalt is included into this. And basalt is like a running joke because people tend to guess basalt on questions that they don't know for some reason. I'm not quite sure why. And then
It's because throughout the last 2 years of Science Bowl, majority of questions about rock have had the answer basalt.
Right, sure. I would disagree, but okay. In between granitic and basaltic, you're gonna have andesitic, which is like intermediate, and it takes about at least 25% dark silicate material, and it's a major part of volcanic island arcs. And then
Is there a type of rock that's called andesite or something?
yes, I think so. And
It's also in Minecraft.
oh, I don't know. I don't play Minecraft. My brother does though. I might like ask him later, whatever. There's also ultramafic rocks, and it's mainly peridotite. I keep on adding O's. Okay, anyway. And ultramafic basically means it's like has a ton of dark silicate. And ultramafic rocks are not generally found in the crust, but they are a major part of the upper mantle. So this diagram is basically a diagram of like the dark color minerals, the light color minerals, and then how they combine together to create like the different compositions of rocks. Okay, sedimentary rocks. So sedimentary. Sure. Tell me when like you're done copying. You know, you guys could also go to the Google Classroom and look at the PowerPoints. You can also get the PowerPoints from Class Y, and it's good to like look at both. Okay, so sedimentary rocks. Sedimentary rocks are formed from like compaction of sediment, and the technical term is lithification. And so sedimentary rocks, some like, I guess, characteristics are you're gonna find them in like beds. So you're gonna have like an entire like layer of one sedimentary rock. And the reason is because how they're like formed, right? Like they're formed by like horizontal or like vertical pushing down. So it creates like horizontal layers of like the same rock. And also fossils are most commonly found in sedimentary rock because like, for example, if it was under igneous rock, the fossils will get, or the organism would like get disintegrated. Or if it was under metamorphic rock, it would possibly also get disintegrated. And sedimentary rocks, there are two types, so like of how they formed. So first of all, you have detrital. So detrital are from particles of weathered rocks. And the rock names depend on the size and shape of particles. So for example, conglomerate is like the collection of gravel like sized particles, and the particles are rounded, while breccia is the like collection of angular particles, but they're also gravel sized. So or gravel. Yeah, gravel. Okay. And then shale is going to be the most common sedimentary rock, and it is a detrital rock. You also have chemical/biochemical sedimentary rocks. So they're made from like when minerals are dissolved in water and then they get to a certain point and they start precipitating out. And also you can also have chemical or like biochemical sedimentary rocks formed from like shells and stuff. So like an organism took the minerals in water, used it to make a shell, and then the organism died, and then you have leftover shells/hard parts that got like mushed together. And you can also have like deposits of stuff. So like, for example, salt. And like the salt kind of gets together. And then you have like rock salt. And then lastly, you have like organic sedimentary rocks. So you can't really term it as like coal is special, okay? It's like the only like completely like made out of plant sedimentary rock. And so coal, like it has a whole process. So first of all, you have to have like peat. And then after you have peat, because there's like little oxygen in it, the stuff doesn't decompose. And then it gets like compacted. So it turns into lignite. And then it gets compacted even more. And then it turns to bituminous coal. And then it like undergoes extreme pressure to the point that it's like it turns into metamorphic rock. And that's called anthracite. So peat is like partially altered plant material, and then lignite is going to be like soft and it's also brown, and bituminous coal is soft but it's like black, and then anthracite is like super hard because it's gone through like metamorphism. Oh, also like energy on Science Pool really likes to ask about coal. Question, comment, someone said something.
You just went to the next slide. I just wanted you to stay on this one for a second.
Oh, cool. Can I move on now?
Yeah, sure.
Okay. Metamorphic rocks. Metamorphic rocks all have a parent rock. So like the thing that they got metamorphed from. So metamorphism can be caused by heat, confining pressure, differential stress, or chemically active fluids. Now, what you're going to want to differentiate between is like confining pressure and differential stress. So confining pressure is basically you have pressure on all sides. So it basically turns a larger cube into like a smaller cube. But the cube is like proportional, right? Because like it's still a cube. But differential stress is when like there's like large pressure from like one plane. So for example, it was a cube and you put differential stress on it, it's going to turn to like a rectangular prism. And so metamorphism can be, so you have like two types of metamorphism: contact metamorphism and regional metamorphism. So contact metamorphism is like when a rock gets like close to magma, but it's not going to be like in magma, because then it would turn into magma, which would make it igneous. But when it gets near like heat, it's going to like cause the rock and the crystal stuff to change. And then you have regional metamorphism, which is caused during mountain building, and it's just because of like super high pressures. And as the rock is pushed further into like the Earth's crust, it's going to cause increases in temperature, which also causes metamorphism. And then metamorphism, like you're going to see like metamorphic rocks generally have two types: foliated and non-foliated rocks. So can someone tell me like which rock is foliated? Because we kind of discussed foliation later, previously. Is someone trying to talk?
I think the second one is more foliated because it looks more layered.
Yeah. So basically foliation is like layered. And what happens is like certain the particles are like randomly oriented, right? But under pressure, they like cause layers of like different like minerals to kind of like congregate together. So then you get these layers. So this is non-foliated and this is foliated.